Welcome to this next video in the playlist on ring theory. In this video, what we're going to talk about is the evaluation homomorphism for polynomial rings. Okay, now this is a very simple topic. This video is going to be very simple. However, it's a topic that people often think is completely and utterly trivial. Okay, and it doesn't quite deserve that title. Okay, it is simple, but it's not completely and utterly trivial. It does require proof. Okay, so the evaluation homomorphism, what we're going to do in this video is we're going to discuss what that is, and then we're going to prove that indeed it is a homomorphism, and people usually regard it as totally trivial that it's a homomorphism and don't usually bother to prove it, but I am going to prove it here because it does require proof. Okay, so firstly then, what is the evaluation homomorphism? Okay, so this is all about polynomial rings, so we might as well start the setup by writing out a polynomial ring. So we're going to take some non-zero commutative ring, capital R, and we're going to generate the ring of polynomials over that non-zero commutative ring, R adjoin X here. Okay, right, and now let me describe then the evaluation homomorphism. So the evaluation homomorphism is going to be a mapping from the ring of polynomials over the ring capital R into the ring capital R. So to write this down, let's call our evaluation homomorphism phi here. Okay, and it's going to be a mapping from the ring of polynomials R adjoin X into the ring capital R. Okay? Right, and the way that this mapping is going to work is that it's quite simply going to pick some element of the ring capital R, and it's going to send all polynomials onto the value in the ring capital R, which is the polynomial evaluated at that element of the ring. Okay, and we need to discuss rigorously what it means to evaluate the polynomial at a certain element, because of course you know from classical algebra, and that's usually why people think this is trivial, because they have a very good understanding of this from classical algebra. Okay, you know from classical algebra what it means to evaluate a polynomial at a certain value, but we need to rigorously define that. Okay, and that's really what this is all about. It's just about evaluating polynomials as a certain value. Okay, so right, so this mapping phi then, it is going to be the evaluation homomorphism for a certain value. So we're going to need a certain value. So let's say alpha is some element of the ring capital R. Okay, then if we want to make this evaluation homomorphism for this value alpha, then the way it will work is it will quite simply send all polynomials onto what that polynomial evaluated at alpha is actually going to be equal to. So if you like, you can subscript this phi here with alpha. It's going to be the evaluation homomorphism, which is going to evaluate all polynomials at the value alpha. And this is going to work no matter what alpha you pick. So you can pick whichever one you like, okay? Any alpha from your ring capital R, it will always be a homomorphism. Okay, so let's define how this is going to work then. Okay, so put shortly, the way this is going to work is it's just going to take any polynomial p of x and it's going to map it onto p evaluated at alpha, but we need to define rigorously what this actually means. What does it mean to take a polynomial and evaluate it at alpha? So let's look at this in a bit more detail. Okay, so I'll write this out again, written more longly but more correctly. It's going to take a polynomial, and a polynomial will look something like this: the sum over I of pi x to the I, where of course these coefficients, these pi's, are all from the ring capital R. Okay, and where's it going to send this polynomial? Well, it's going to send it onto the sum over I of pi, and then you're going to substitute in for x, alpha I. Now this looks deceptively simple. Okay, really what has happened here is a very big change, and I want to stress in this video, this is the main purpose of this video, to stress what a big change has actually occurred there. Okay, on the left hand side, this polynomial, this is just a symbol in the ring of polynomials over that ring capital R. Okay, it's just a symbol. The powers of x, they are just placeholders. Okay, the pluses in between the different terms, those are just symbols. Okay, you've just created this symbol in this way, where you've stuck a few coefficients in front of powers of x which are meaningless, they're just placeholders. Okay, and created this symbol. Okay, so writing this out explicitly, it looks something like this: p0 plus p1x plus all the way up to, let's say, the degree of the polynomial is n, so pn x to the n here. Okay, but all we've done is stuck these elements of the initial ring in front of these powers of x. We're not multiplying them by the powers of x, we've just stuck them in front of them. Okay, the powers of x are just symbols, they're just placeholders. The pluses in between, they are just symbols. Okay, this is just one great big symbol for the element of the polynomial ring. Okay, so here, this sum, really it just means create this symbol where you've put pluses in between these different terms there. Okay, so it goes from having this symbolic meaning, this sigma symbol goes from having just a symbolic meaning, it tells you how to create this symbol in the polynomial ring here, and now over here it has a completely different meaning. Here, all of these things actually do mean plus and multiply in the initial ring, capital R. So now, writing this out explicitly, this is going to be p0 plus p1 alpha plus all the way up to pn alpha to the n. But now the multiplication really is a multiplication. We haven't just stuck the coefficient in front of x anymore to create a symbol. Now, when we've got p1 next to alpha like that, that actually means multiplication in the initial ring, capital R. When I have alpha to a certain power here, that actually means multiply alpha with itself a certain number of times in the initial ring, capital R. So I'll denote everything to do with the initial ring, capital R, in green here. The plus symbols here, these all mean add these terms together in the ring, capital R. Okay, so it has completely changed its meaning now from this very formal notion of a polynomial, which was just a symbol. Okay, we just had these powers of x as placeholders and we just stuck coefficients in front of them to create a symbol like this. Okay, the ring of polynomials was just a set of symbols with an addition and multiplication law defined on it, cleverly from the addition and multiplication laws defined on the initial ring, capital R. Okay, and now we've taken this very abstract and formal notion of a polynomial, and now the addition and the being next to each other and the powers all actually are interpreted in terms of addition and multiplication in the initial ring, capital R. So we have completely changed the meaning of this, basically. So there is a big jump from here to here. Okay, and really, if there's one thing that I would like to communicate to you in the video, is just how big a jump there is there. Okay, how non-trivial this is, really. Okay, right, so there's our mapping, our evaluation homomorphism. So by the way, this mapping phi subscript a, this is what is known as the evaluation homomorphism, and you could, if you like, call it the evaluation homomorphism at the element of the initial ring alpha. Okay, so because we're evaluating our polynomial at alpha. Okay, so we've acknowledged, hopefully now, that it is a mapping from the ring of polynomials R adjoin x to the ring, capital R. Okay, and actually I probably should just talk you through why that is. All of these answers are, of course, going to be in the ring, capital R. Alpha is in the ring, capital R. All of these coefficients are in the ring, capital R. Okay, I should just put that down somewhere. Pi is an element of the ring, capital R. Okay, so we're just adding and multiplying elements of the ring together. Okay, and of course, what we'll end up with here is just another element of the ring, capital R. Okay, so you will end up with just an answer in the ring, capital R. And indeed, you can do this for all polynomials. You come up with any polynomial in the ring of polynomials with coefficients from the ring R, and I can evaluate it at alpha and send it on to some element in the ring, capital R. Okay, what remains to be shown now is that this is actually a homomorphism. It's a ring homomorphism. We've got a mapping from one ring into another ring. Let's now check that it's a homomorphism. Okay, so there are 3 criteria that we need to prove are going to be true. Okay, additive compatibility, multiplicative compatibility, and the fact that the multiplicative inverse, sorry, not multiplicative inverse, multiplicative identity in the first ring is mapped onto the multiplicative identity in the second ring. Okay, let's start off with additive compatibility. Okay, so the way I'm going to do this, the way I'm going to prove these things, is with a lot of colour. I'm going to colour code things, okay? I think whenever you're doing homomorphisms, it's good to colour code the addition and multiplication operations so that you know when you're talking about addition and multiplication in the domain ring, and you know when you're talking about addition and multiplication in the codomain ring. So let's colour everything to do with the ring capital R in green, okay? And everything to do with the polynomial ring over the ring capital R, we'll have that, I think, in orange, okay? So addition and multiplication in the polynomial ring will be coloured in orange. Okay, so what we want to prove then, and I think I'll just drop the alpha, I will just denote this phi, okay, just to avoid having to write that cumbersome alpha. Okay, I'll make it look simpler. Okay, we want to prove additive compatibility, so let's start off with additive compatibility. So we take two elements of our domain ring here, and two elements of our domain ring are just polynomials, okay, with coefficients from the ring capital R. So let's take two polynomials, so we'll take the polynomial a of x and b of x, so let's have a here, ai x to the I sub over I, okay, and we add the two of them together in the domain ring. Okay, so this is addition in the ring of polynomials with coefficients in the ring capital R. So the sum over I of, let's say, bi x to the I here. Okay, and then, so we add the two things together in the domain ring and then ask, okay, what will this be mapped onto in the codomain ring? Then additive compatibility, if it was true, would say that this was equal to, firstly map the polynomial a of x into the codomain ring here, so take phi of the sum over I of ai x to the I here, okay, and then add it to phi of the polynomial b here, sum over I bi x to the I, where of course this addition now is no longer addition in the domain ring, but addition in the codomain ring, so this is addition in R, so it should be in green there. Okay, so if additive compatibility is true, this is true no matter what polynomial, what two polynomials you pick here, a of x and b of x. So we don't know this is true, so I'll put a question mark above the equals there. Okay, so this is what we want to prove is true. So let's do this. Let's take the left-hand side, develop it a little bit, take the right-hand side, develop it a little bit, and show that they're equal to one another. So let's think about the left-hand side here. So we've got these two polynomials added together. How do you add two polynomials together in the ring of polynomials with coefficients in the ring capital R? Well, of course, you do it component-wise. You just add the coefficients in front of the same power of x in the ring, which is the coefficient ring, and then put that in front of that power of x. Okay, so to add these two together then, what we'll get is the sum over I of ai plus bi, and note that addition now. That addition is addition in the ring capital R. You're adding the coefficients, which are obviously elements of the coefficient ring, together in the ring capital R, and then that will be in front of x to the power of I here. So we're now taking phi of this. Now, so that's equal to that. Now, of course, we can just apply the definition of the evaluation homomorphism phi, and we're imagining that it's still a evaluation homomorphism where we're evaluating at some arbitrary element of our coefficient ring alpha. Okay, so applying the definition then here, this will be sent now onto the sum over I of ai plus bi. And just to highlight the change in meaning, I would actually put a time symbol there, and we'll have alpha to the I. Okay, and that multiplication now is multiplication in the initial ring, capital R. This addition is obviously still in the ring, capital R. Okay, the taking to the power is done in the ring, capital R, and this great big sum here is now done in the ring, capital R. So previously, this sum here was just that symbolic sum, and I'll highlight symbolic sum in yellow. So whenever I underline a sum in yellow, that will be our symbolic sum. Okay, so this was just the symbolic sum, but now it's turned into the actual sum in the coefficient ring, capital R. Okay, so this is what phi of that is equal to. Now what we'll do is develop the right-hand side here. So let's ask what is phi of a of x and phi of b of x, and then let's add them together in the codomain ring, capital R here. Okay, right, so phi of this polynomial a of x, so just apply the definition. Again, let's colour it in. So this was just symbolic sum, okay, a boring symbol here, and now what we've done is we've actually turned this into a real sum in the coefficient ring, capital R here. Okay, I apologise for continually moving between calling this the coefficient ring or the codomain ring. Okay, those two words can both be used to describe this, because of course it is the codomain ring of the evaluation homomorphism, and it's also the coefficient ring of the ring of polynomials here. Okay, sum over I of ai alpha to the I here, and of course again this is sum now in the actual ring. This multiplication here is multiplication in the actual ring. I know I forgot to put the actual times symbol in there. This alpha to the power of I, that's in the actual ring, capital R now. Okay, and then what we're going to do is we're going to add that thing in the actual ring. Okay, so this is going to be added in the actual ring, and I might just put some brackets in here, so we'll have some brackets around that, to this thing here. Okay, so again, evaluating b of x at alpha, we'll get the sum over I of bi alpha to the I. Okay, and again, we've changed the meaning now. This is sum in the actual ring, capital R, whereas this was just the symbolic sum. Okay, we've got multiplication here of bi with alpha to the I, which is in the actual coefficient ring here. Alpha to the I is done in the coefficient ring, so that is equal to that. Now, of course, what we've got here is a great big sum of loads of things, okay, loads of ai's times alpha to the i's, and here we've got bi's times alpha to the i's here. Now, because addition in our ring, our coefficient ring here, can be relied on obeying associativity and commutativity, we can muddle this up as we choose. Okay, so we can get the same powers of alpha next to each other, and then of course what we can do is apply distributivity that will work in this ring to factor that alpha to the power of I out. And of course, I hope it's not too big a stretch of the imagination to understand that this can be turned into this very easily just by bringing those terms that have the same power of alpha next to each other, okay, and factoring out that power of alpha, you will end up with this. Okay, so I hope that's not too big a stretch. Okay, right, so there, we have indeed showed additive compatibility, equals, 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 equals. We've gone from here to here. So yes, I can put a tick there. It is true that this is equal to this. My arguments didn't rely on these polynomials having any special properties, so it's true arbitrarily. Okay, so indeed, this map is compatible additively. The domain ring and the codomain ring are actually additively compatible. Okay, so it's looking good for being a ring homomorphism. Let's now go to the next biggie, multiplicative compatibility. Okay, so same procedure all over again, just multiplication this time rather than addition. Okay, so we want to prove that phi of the sum over I of ai x to the I here times the sum, and now it's more convenient when you're doing multiplication to use a different index, whereas in addition it's nice to use the same index. Bj x to the j here, so these are just two polynomials, and of course we're multiplying them there in the actual polynomial ring r adjoin x. Okay, we want to prove that this is equal to phi of the polynomial a of x, so the sum over I ai x to the I here, multiplied in the codomain ring, the coefficient ring, so I'll colour that in green here, with phi of the polynomial b of x, which is the sum over I, j, we'll keep our same index, bj x to the j here. Okay, so that is what we need to show if multiplication is going to be compatible. So again, I'll put a question mark up there. So same strategy as before, we're just going to develop both sides and show that they're actually equal to one another. Okay, so let's start by developing the left-hand side here. Okay, so let's start by multiplying together these two polynomials. So this relies on us remembering how to multiply two polynomials together that are in the polynomial ring where the coefficients are in the ring capital R. Okay, so how do you do that? Well, remember the best way to understand multiplication of polynomials is to think about the fact that once you've defined addition, you can take any polynomial and you can write it as its decomposition into monomials. Okay, so the instant you define addition on the set of all polynomials with coefficients in the ring capital R, you can then say, if I have an arbitrary polynomial like this, I can view it as a decomposition into monomials. Okay, so this is another important change of interpretation. Remember, initially we saw this sum as a symbolic sum. It was just symbols. Okay, the x to the power of things were just placeholders. We put coefficients in front of them from our ring capital R, and then we put pluses in between them just because we like that symbol. Okay, but now it actually gains a bit more meaning than that. Okay, and I'm talking about a different meaning than actually what's given to it by the evaluation homomorphism. Even in the polynomial ring, it can be given a different meaning, which is that it can now be thought of as actually being a sum of monomials. Okay, so monomials are polynomials, and this polynomial, the sum over I of ai xi, you can view it as lots of those monomials, which are polynomials, added together according to the addition law that's defined on the polynomial ring R adjoin x. Okay, so we can now view this, and I'll underline in orange, as a sum in the polynomial ring rather than just as a symbolic sum. Okay, so the instant you define addition, not before you've defined addition, before you've defined addition you just have to view it as a symbol. Okay, but once you've defined addition, you can actually view it as being a decomposition into a sum of monomials. And that's actually very helpful for understanding multiplication, because it means that we only actually have to define how to multiply two monomials together. Okay, and the way that we define multiplication of monomials is you multiply the coefficients in front of those monomials in, of course, the coefficient ring, and then you just add the powers of x. Now, the instant you've defined how to multiply two monomials together, it instantly forces you to define multiplication of polynomials in a certain way, because, of course, you want multiplication to obey distributivity if it's got any hope at all of being a ring. Okay, so what you can do is view this as a decomposition of monomials, view this as a decomposition of monomials, and then you just have to distribute everything out. So expand the brackets, and then you'll get loads of products of monomials. Okay, then you need to add all of those products of monomials together in the polynomial ring, which is something we've assumed we've already defined. And then if you can do that, you'll get the answer as to what the two of these polynomials multiplied with one another is. Okay, so remember, that's just a reminder of how we define multiplication of polynomials in the ring of polynomials. Okay, so this will become then the sum over I, the sum over j, and this is why we like to have different indexes for the two polynomials. And then it will be ai times bj, okay, and then you'll have x to the I plus j, and I do apologise, this pen is running out, so we will have a break here, okay, an unforeseen break, whilst I get a new pen, and we'll continue this discussion in the next video.